So we have to start the section rearrangement of series. I was interested in this. Not the rearrangement of series is a very exciting one. However, the root test and ratio test, but I want now, you have done nth term test, comparison test. What are the other? Integral test cannot be done. There is a test called integral test. You have to know bit of integration to do it. We don't have it. Cauchy condensation test done, comparison test done, and term test done. Term test done. But here you have rearrangement of series. That is terribly exciting section. But I am interested in finishing all the tests. Root test and ratio test remains. So let's do that and come back to rearrangements. Rearrangements, because it is there just for fun, a little thing. Can I say it to did I forget something? Did I? Let's see. I wrote my book also. Even though I am postponing rearrangements, just to show you something. Before I go there. Does book have enough problems? No. Let's consider the series. I will come to the root test and ratio test. This is an alternating series and it converges. Actually, this is equal to L into natural log to 1. It's not important for us. So assume this is equal to S. Just to show you now. Next, what I will do, I take a rearrangement. rearrangement is 1 over 1, then I write next to minus terms. Minus 1 half, minus 1 4. Now I have 1 over 3, next 2, minus 1 over 6, minus 1 over 8. Got the thing? Next I write 1 over 5, minus 1 over 10, minus 1 over 2. Like this, you got the rearrangement. After every positive term, write the immediate negative terms. Now I put parentheses here. I'm also out of touch actually. 1 over 2 minus 1 over 4. No? 1 over 3 minus 1 over 6 is 1 over 6. No? Minus 1 over 8. Then 1 over 10 minus 1 over 12. Like this. Right? I take 1 half out. 1 over 2, oh, 1 over 1 minus 1 over 2, plus 1 over 3 minus 1 over 2, plus 1 over 5 minus 1 over 6. Right? So, if this is S, this is
Yes.
S, so this is S over 2. I mean, this is correct. I mean, this is not magic. This is true. When you rearrange terms, you can end up with that. Actually, this one is ln2, this one is ln2 divided by 2, just by rearranging. So, this shows that rearrangements do amazing things. Amazing things. I just want to show you. Of course, now you have the book. I guess I don't know whether I have enough. Cannot remember because almost. Another, I don't remember. This is the book. Another rearrangement I have considered. 3s by 2. So this one says, if you add in the normal order, you get natural log 2. If you do this rearrangement, you get natural log divided by 2. Another one I have written in the book, 3 times natural log 2 divided by 2. So, one day I asked, you replied. I asked, this is equal to 1. You told me this, if this is x, you said something.
Then x equals 9.999.
10x?
Yeah.
You multiply 10. That's 9, right?
Yeah.
9.
Then you subtract. You get
9x equals
9.
no?
Yeah.
9. This is equal to 1. Now, this is, although we got it, what we wanted, this is not a good way to do it. I mean, it's not. Number one thing is here, how do we know that? If you just write numbers, how do you know that it converges? Before we do other gadget things, we have to make sure that it is a convergent series. How do you know that this one is convergent? Because can you remember in the very first, he had one chapter at the beginning, wrong things he has. This is one of them, by take your method. We have to make sure that actually there is a real number x. In maths, suppose somebody writes sigma 1 over n is equal to x. You cannot write like that because you have to make sure that sigma 1 over n is a real number and it's a convergent thing. Like that you have to know that this is convergent. How do I know?
Because it's less than 1. And it's an increasing number.
Now we have root test and ratio test are the last tests that we are going to do. That's why I want to do it today. Next day when I come, I would like to go through the rearrangements of series. It's very exciting. I mean, we should not do this method. I mean, I'm not saying, and remember, if you do this way, you can run into false conclusions. According to the first chapter, actually, how do we know that this is a real number? How do we know?
We can say it is epsilon close to 1. Epsilon close to 1.
Oh, good. Epsilon goes to 1. So, I cannot remember actually. Epsilon goes to. But you are good. I mean, you have some kind of memory. But if somebody asks you, when you are in the train or bus, a young boy asks you, oh young girl, how do you know that this is a real number? There must be an answer. He does not know epsilon close thing. He or she. Cannot say that today.
Can you say by proof by contradiction?
Prove that it's not a real number, then what you can.
That's a good one. If it is not real number, what can you do? What can you do? Anything? So think about it. I just wanted to point it out because whatever we do, we should be dealing with real numbers. Because I have seen somebody, he got a degree also from somebody who does not know mathematics. He writes sigma something something, say things. This is not a convergent series. So anyway, the guy, I told the advisor, he died, I think. that these are not real numbers, these are not convergent series or divergent series or anything, nothing. But he didn't care. He gave the PhD, not the PhD, some degree. Some degree. Okay, so I'm going to quit. I presented this thing to show you that clear elements are important. It does amazing things. It does amazing things. So let's come see whether you can answer this question by next day. Because I usually don't do it, because I always try to go mathematically correct statements. I mean, there are times at which here it works, no? Sometimes it works, but it's not a good thing. See this. Now, for instance, now you have enough knowledge. Log n going to infinity to conclude whether this is convergent or not. You don't have to do it now. You see what I said? I am saying you have enough knowledge now to decide whether it is a real number or whether it is convergent or not. Let's not do it now and let's go to in other books actually, including mine, rearrangement of series is the last thing they do. But in this book, there itself different. So here let me see. Root test. Root test. You need root test first. Ratio test, yeah. Follows. Again, that is another difference. Other books they do ratio test first and do root test later. Doesn't matter how you. Theorem. This is a very important one. Root test. Let sigma A and B and series of real numbers. Series of real numbers. And let alpha equals lim sup. He says mod A n raised to the power 1 over n lim sup. So given any a n, lim sup always exists, unlike limit. So this statement makes sense. Part A, if alpha less than 1, then the series n going on to infinity, A n is absolutely convergent. Let's prove it first and then go to the second one. Let's see whether we can prove. Now you need to remember we have done n-term test, means that limit of n is not equal to 0 or n doesn't have a limit, series is divergent. Sorry. Yes. Then another test we did was comparison test. If a bigger series, the import, by the way I say is, sounds not good. If Bn greater than or equal to absolute An, however, you cannot apply, I say, if a bigger series is convergent, smaller series is convergent, that's in fact not true. One can say is, if a bigger series is convergent, then the smaller non-negative series is convergent. Because for instance, say, you say Bn 1 over n squared, this is convergent, minus 1 over n here, this is convergent, but this is not convergent, you have to have absolute sign. Anyway, we did the comparison test. What else we did? Cauchy condensation test, alternating series test. Now root test is on the board. Thereafter we have ratio test. Then we will have done all the tests. Then you should be able to do any problem. I don't know whether
Theoretically.
Theoretically. No, you will, both of you will be very good at testing. I know that. But it takes time because this book actually does not have enough problems here. So it's a different book. Proof, okay. So sigma n is absolutely convergent. Alpha. So suppose alpha less than 1, no? Then I can say then there exists say some but say capital N belongs to Z plus such that what is it? To the 1 over n is strictly less than alpha plus 1 minus alpha divided by 2 for each n greater than or equal whatever, doesn't matter. Like this. This is from Lim-Suk. Lim-Suk an equals capital lambda if and only if given any epsilon there is a capital N such that an is really less than lambda plus epsilon for each n greater than n, and for each m belongs to Z, there is a n belongs to Z plus such that n greater than m and an greater than lambda minus alpha, two conditions. So if you simplify this thing, what will you get? Alpha plus 1 divided by 2, no?
Yeah.
Thus, let me write it thus. THU is thus mod a to the 1 over n is strictly less than 1 plus alpha divided by 2 for each. Simple and greater than capital A. Let's write greater than. Oh. Thus, mod a n is strictly less than 1 plus alpha divided by 2 to the power n for each n greater than or equal to n. Now what can you say?
1 plus alpha over 2 is less than 1.
One.
So 1 to that thing to the power n, when you take the limit it goes to 0. So a must limit of a must the limit of mod a should equal 0.
So what?
Therefore the sum should be the series converges.
Negative 10 marks. Now, can you correct him? He said it's not. I gave him negative 10 out of positive 10. Somehow he noticed something. He noticed this thing is less than 1. That's very good. Whatever was said after that is not correct.
Just because it is less than 1, we can say that. Oh no. The limit goes to 0.
Sigma 1 over n diverges even though limit of 1 over n is equal to 0. By observing limit of n is equal to 0, you cannot say anything about the convergence or divergence about sigma a. But he made the observation that this number, actually this is greater than 0 also. No? This is greater than 0. Actually this is exactly greater than 1/2. But now you need to come to positive side, and now I have given you only negative 10. But you have observed the most important thing. Most important thing you observed. Let's write that also. Notice that 1 plus alpha divided by 2 from here greater than 0, here strictly less than 1. Your observation was because this sequence converges to 0, so does this sequence. Sorry, yes, so does the sequence. And somehow you have to reverse negative 10.
n is less than equal 1 or alpha power n. So the right hand side thing converges to 0. Therefore mod a converges. So a n absolutely converges the sum from the.
Now marks are negative 20. We are interested in sigma A, not the sequence A. These are two things. This is a series, this is a sequence. And in my notation, it doesn't matter.
1 plus alpha to the power n, the sum of it converges
Why?
because it's a geometric series and the common ratio is less than 1 the most of it. Therefore, the absolute the sigma into 1 to infinity a in absolutely continuous.
Since 1 plus alpha divided by 2 greater than 0 less than 1, the geometric series. Luckily you notice that, otherwise you go home with negative 20. The geometric series sigma 1 plus alpha divided by 2 raised to the power n going 1 to infinity converges. Thus, I'm asking you now this series converges, not the sequence. Thus, by what?
By the comparison test.
Very good, thus by comparison test. What they converges. That is sigma n converges absolutely. Now it is correct, no? Now it is correct. Okay, so alpha less than 1 case is done. Right? Alpha less. So this is very important. Now, if you want to apply comparison test to another series to show that the given series is convergent, you need to come up with your Bn from somewhere in the world. Here, you are not going to anything else. You are going to the limits from the nth root of given thing. Can you see? In order to apply comparison test, you go outside and look for something given bigger than the given series and which is convergent. Here, you don't go anywhere. Right? Shall I reach? So, very important series, very important test, root test. Now, if alpha greater than 1, then the series sigma n is, how has he written? Then the series is not conditionally convergent. That's how we understand. It's not conditionally convergent. Not conditionally convergent, he says, and I give something more, not conditionally convergent, and hence cannot be absolutely convergent. And hence cannot be absolutely convergent. Can I erase the proof? And you see, I told you geometric series is, although innocent, you use geometric series to go through this. Um, hmm. Now suppose alpha is strictly greater than 1. Now how the proof goes. How does it go? Let see epsilon equals alpha minus 1 divided by 2. Alpha greater than 1. Right. Now what? How will you say this is not convergent? What is it? This is Lim-Su. You are working with Lim-Su. When to show that when alpha is strictly less than 1, the series convergent, Lim-Su equals alpha has two statements. No? We use the first one. Given any epsilon, there is an integer, say capital N, such that for each n greater than capital N, a n less than or equal to alpha plus epsilon. We use that.
I'm going to make a subsequence of a such that it is not convergent to 0. Therefore, the sequence of an doesn't converge to 0. Therefore, it does not. The sum of an does not converge. That's my idea. To make that the sequence like epsilon greater than 0. To put the first term, there exists the capital N greater than 1 and simple n not greater than 1 such that n is less than alpha minus epsilon. So maybe
A is less than.
n is greater than then I use the other one.
Do you understand what he is trying to say? Lim sup has the second condition is what? Epsilon is given. Is it given any? No, for each n belongs to n. So is it plus? What? There exists. Because I am used to write capital N always. There exists. M belongs to Z plus such that M greater than N Xn, what is it? Mod A into the 1 over n is strictly greater than alpha minus 1 minus alpha divided by 2. This is minus this way. So this is equal to alpha plus 1 divided by 2. That is the condition. So using that, what can I say? Now can you complete the proof now? That you need to use that. That is correct, no? So for instance, if you, in my case I am going from 1 to infinity. So say, notice that actually from the Lim sup picture, if you take any n here, there is m here, it is above here. Again, if you use m here, again something bigger, you get the subsequence greater than alpha plus 1 by 2. Notice that. Anyway, because it is the first time, let me write that there exists n1 belongs to Z plus such that n1 is strictly greater than 1 and alpha mod a n raised to the power mod a n n1 raised to the power 1 over n1 greater than 1 plus alpha divided by 2. Again, there exists n2 belongs to Z plus such that n2 greater than 1 and mod of a n2 raised to the power 1 over n2 greater than alpha 1 plus alpha by 2. Right? Once again, there exists n3 belongs to Z plus such that n3 greater than, this is not running one, n3 greater than n2 and mod a n3 to the 1 over n3 greater than 1 plus alpha divided by 2. So you get a sequence this way. Proceeding in this manner, I will use this easy language, proceeding in this manner. MA double N ER, what am I writing? There exists a strictly increasing sequence of integers. It's a strictly increasing sequence of, sorry. Nk of integers, natural numbers for instance, such that mod A n k raised to the power 1 over n k greater than 1 plus alpha by 2 for each k. Now I am done, right? Because this one says thus mod A n k is strictly greater than 1 plus alpha divided by 2 raised to the power n k for each k. And 1 plus alpha divided by 2, this is greater than 1. So, something you said, therefore limit of A and K is not 0. Thus, lim K mod A and K cannot be 0. Actually, strictly greater than 0. Thus, lim n tends to infinity. Mod A is not equal to 0. Right? Then by 0 test, I guess that's the word book uses. So in my way, by nth term test, the reason to say nth term because we are doing nth term, yeah, is not equal to 0. Thus sigma n like this. Right? So we have proved that if alpha less than 1, series converges. If alpha greater than 1, series diverges. You agree with the proof, no? Everything is here.
Sir,
Yes?
sir, you said that the proceeding in this manner is the easy case. So
No, I guess easy language. I mean, if you want to write rigorously, you have to use induction.
yeah, okay.
This is not, for a solution in an exam, that is enough. You can say proceeding in this manner. But if you want to be very pedantic, real crystal clear, then you have to use induction. Then you need to say here, suppose some say n1 up to nk has been chosen, you will have to go to that language. So, but that doesn't improve your analysis knowledge, it improves your writing. Alright? Got the picture? Shall I rest? So we have proved both of them. After we do the ratio test, you should be able to do any problem. I will come with them. Whole bunch of problems. By next day or month, maybe next Wednesday, because I should finish the rearrangements next day. I jump to this thing because I want to finish. Fish. You need to do a couple of 1 or 2 examples actually from. What is the next thing? He says, if alpha equals 1, we cannot assert any conclusion. If alpha equals 1, then we cannot my spelling not English. Somebody will call and ask, from where did you learn your English? And we cannot assert Any conclusion? Because you are given a series to determine the convergence or divergence of the series. If by any chance lim sup less than 1, then you can say series converges. If it happens to be alpha greater than 1, then you know series diverges. But if alpha is equal to 1, you cannot say anything. So I have to give some examples. For instance, let's see, let n equals 1 over n. N is equal to 1 over n for each n. Then lim nth root of an. Have you done it by then? I'm going to write like a big guy, but you haven't done it yet. Nth root of 1 over n you haven't done, no? And because I see it is on the next page. I can see we have. I think that we can use this. Anyway, I will take a rain check and say using that. Then lim sup of nth root of n is equal to 1 will be shown. I guess not today. Being safe side, I will write will be shown later. So if you take n to be 1 over n, then lim sup 1 over n is equal to 1. Of course, we have to do it. And lim sup of this thing is equal to 1. We know that sigma 1 over n diverges. Sigma 1 over n. Now wait. Say n is equal to 1 over n squared. What is n belongs to z plus? Then lim sup n tends to infinity. What n to the 1 over n is actually lim sup of one over n squared raised to the power 1. This is also equal to 1. Will be shown later. We know that sigma 1 over n squared converges. We have proved it 2 ways. One way, like A-level method I did today on the board, and the other one is applying that sigma 1 over n to the q converges if and only if q greater than 1. Here you have 2 greater than 1, therefore this one converges. So that's we have completed the root test. So actually you are, how to see, I did not, because these things since I know very well, I don't follow the book. Because first chapters, I don't know anything, then I have to go through the book. Right? Shall I wish? Clear about? sigma 1 over n divergent, sigma 1 over n squared convergent. So, however, lim sup of a n to the 1 over n is equal to 1. When it is 1, it can diverge. When it is 1, it can converge also. That is why then we cannot assert any conclusion. The reason to say so is, see, this time lim sup is 1, series diverges. In this side, lim sup is again 1, but the series converges. Right? So, I guess we should do some examples, but let's see whether he has done some examples. No, he's like a big guy. He is like a big guy.
It's exercise.
Eh?
He's given us that one, it's an exercise.
Okay, now let's go to anyway. Lemma 7.5.2. I don't know why. Ratio test. Do we need it? Anyway, because of it is inside the book, I will go to lemma 7.5.2. Now root test is clear, no? So when you are solving a problem, if the other tests don't work, if you want to apply the root test, and if by any chance, if it happens to be lim sup of the nth root of a n is 1, you don't have anything. That's the bad thing. That is the bad thing. Then he has kind of a Okay, what is his lemma? C and B is equals of question numbers. Let C n, he says, n going m to infinity. B is sequence of positive numbers. Then we have lim inf Cn plus 1 over Cn less than or equal to lim inf and nth root of Cn less than or equal to lim sup nth root of Cn less than or equal to lim sup Cn plus 1 over Cn. N tends to infinity. N tends to infinity. N tends to infinity. We don't have to prove this thing. We know that. So even though we have to prove the first inequality and the last inequality. I don't know again, I want to go to. Is it cold to you guys? Not that. Mata hita hai here. Kaman ek nisa. That's the thing. Can you see? No. I cannot say what I wanted to say. Now, okay, let's go. So I have to prove these two, not prove this one and this one. If by any chance this is infinity, nothing to do. Ne? If lim sup n tends to infinity, Cn plus 1 over Cn is infinity, there is nothing to do. So, suppose that lim sup Cn plus 1 over Cn, but Nirvishwa is strictly less than the mechanical money. Let lim sup Cn plus 1 over Cn is equal to lambda. Is equal to lambda. Then I have to prove that this is the less than or equal to lambda. No? How will I do it? How will I do it?
So can we prove that for each n, C 1 plus, sorry, C n plus 1 divided by C n is greater than or equal to nth root of C n for each n?
I don't understand what to say. I took this one as lambda, and now I have to prove this one is less than or equal to lambda. If you want, we can write this sort of things. No, let epsilon greater than 0. Then there exists, say capital N belongs to N, such that for each n greater than or equal to capital N, Cn plus 1 divided by Cn is strictly less than lambda plus epsilon. Hence, Cn plus 1 divided by Cn less than or equal to lambda plus epsilon. Cn plus 2 divided by Cn plus 1 also less than or equal to lambda. Less than lambda plus epsilon. Cn plus 3 divided by Cn plus 2 is strictly less than lambda plus epsilon. Right? Right? Far away, Cn plus n divided by Cn plus n minus 1 lambda plus epsilon. Right? Okay. Now I multiply. There are, I want to make sure 1, 2, 3 n inequalities here. So this Cn plus 1, this Cn plus cancel out. This Cn plus 2, this Cn plus 2, multiplying, because I can multiply if these are greater than 0. Otherwise I cannot. Right? Multiplying. N inequalities. Inequalities we obtain Cn plus n on the top, C capital N, right? Less than lambda plus epsilon raised to the power n. This is true for any n, right? For each. N belongs to the set class. Thus, C n plus n is strictly less than C capital N times lambda plus epsilon raised to the power n for each n belongs to Z class. Right? Now I want to replace n plus n by n, say m. So I will say Cm. My substitution is m is equal to n plus n. Then Cm is strictly less than Cn. N is m minus n. So this is true for each m greater than or equal to n plus 1. Right? Cm is strictly less than Cn raised to the times lambda plus epsilon raised to the power m minus n for each m greater than or equal to n plus 1. Right? Now if you take the mth root, no, let's be right. That is Cn is strictly less than Cn divided by lambda plus epsilon, epsilon be 0, raised to the power n times lambda plus epsilon raised to the power m. This is true for each m greater than or equal to n plus 1. Are you with us? Now let's take the mth root. Thus, mth root, let's be right, Cm is positive, no? I mean, you know this thing, Cm raised to the power 1 over n is strictly less than Cn raised lambda plus epsilon raised to the power n, this whole quantity raised to the power 1 over m times lambda plus epsilon for each m greater than or equal to n plus 1. Right?
So it should be for each simple n greater than or equal to 2m, 2 capital N plus 1. No?
Here,
Yeah.
so I wrote n plus n.
Yeah. There. Over there. For each simple n
Greater than or equal to n plus 1.
2n plus 1.
Why do it?
Because simple n is greater than or equal to capital N.
For which this one is true for each.
Sorry, 2, it should be 2 n. M should be.
This here, why do it? I multiplied this thing, no?
No, not with that thing, just.
Yes.
Yeah.
Why,
Should be-
where did you get to it?
Because simple n is greater than or equal to capital N. So, yeah, on the top.
No.
On the top. No, no.
No, I went right in because there was doing that.
It says
What did it say, Buddha?
on the top, in the middle, there says for each simple n greater than or equal to capital N.
Oh,
So from that, simple n should be greater than or equal to 2n, 2 capital N.
no, what am, it's not this n here. I have n inequalities, simple n inequalities.
No.
When you multiply this side, lambda plus epsilon raised to the power n. This n has nothing to do with this n. Right? Now, you studied somewhere limit of x raised to the power 1 over n, n tends to infinity is equal to x to the 1 over, x is a positive number by the way, x to the 1 over n as limit n tends to infinity is equal to?
Zero.
No, what is the guess? This is a very important limit. If you didn't come to this class, what it will be? X to the 1 over n as n tends to infinity. X is 1. If you haven't come to this class, x is persistent. Now, this is a constant. Epsilon is given, n is, all of these are constants. So, limit of this thing is 1. Therefore, lim sub Cm raised to the power 1 over m. What am I doing? M tends to infinity is less than or equal to, if the limit is 1, then lim sub is also 1. So 1 times lambda plus epsilon. Right? Since epsilon is arbitrary, since epsilon greater than 0, or now I could have written let epsilon greater than 0 be arbitrary. Less than, since epsilon greater than 0 is arbitrary. Lim sub Cm raised to the power 1 over m, m tends to infinity, less than or equal to lambda. Right? So I have proved the right hand side. By the way, this is something you will have to use quite often in analysis classes. this result. Lim in for Cn plus 1 over Cn less than or equal to lim in and root of Cn less than or equal to lim sub and root of Cn and less than or equal to lim sub Cn plus 1 over Cn. Right? So, we have to prove the left hand side inequality then. Right? Can I erase that? Clear? Okay. But today we don't have time to do any problems. We should take this Friday and not enough next Wednesday to finish up the series. Inf. Let's see. Assume will it work? I can just say that in hints in the book. I haven't looked at this sort of thing for many years. Because if I choose, doesn't matter anyway, let's say, assume lim inf n tends to infinity, Cn plus 1 over Cn is equal to lambda. Mu, not lambda.
Yes, sir. Don't we have to assume the condition that if it is negative infinity, that's nothing to prove?
No, you never go to infinity, then you are right. When I was writing, it came to my mind, but I was lazy. Suppose lim inf Cn plus 1 over Cn is equal to 0. So Cn plus 1, Cn polar non-negative numbers, positive numbers, so it will never be negative. So if this is 0, obvious, then there is nothing to do. I was lazy to write anyway, somehow you made me write this. There is nothing to do. So assume lim sub, not sub, but in tends to infinity, Cn plus 1 over Cn is equal to mu greater than 0. It's a real number. Whether proof will work, I can't do because I forgot that to check. Sometimes I get a piece of paper and write something. I forgot to write because I was thinking actually that we are coming here today. Some person will be here, somebody else. We are going to lunch. So I completely forgot to check what should be done to let it happen. Then, let epsilon greater than 0. Then, there it is. Capital N belongs to Z plus, such that Cn plus 1 divided by Cn is strictly greater than lambda minus epsilon for each n greater than or equal to n. Assume epsilon is greater than 0 and is strictly less than lambda. Otherwise we will run into problems. Right? Because this is from limit. Hence, see for each n greater than or equal to capital. Hence you get Cn plus 1 divided by C capital N greater than lambda minus epsilon Cn plus 2 divided by Cn plus 1 greater than lambda minus epsilon Cn plus 3 divided by Cn plus 2 greater than lambda minus epsilon. Huh?
Yes.
Not lambda.
So it is easy to change the mu.
Yeah. On the top side.
Bingo, bingo, bingo.
So there's a
One less.
You notice something, I always take volume sub lambda. Volume means mu. This is my practice. Okay, bingo, 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 bingo. C n plus n divided by C n plus n minus 1 greater than mu minus epsilon. Multiplying by multiplying ELIING the n inequalities we obtain like before it cancels, no? Cn plus 1, Cn plus 1, Cn plus 2, Cn plus 2. Here you get C capital N plus N divided by C capital N greater than, because these are greater than 0. Mu minus epsilon raised to the power n. So, thus, this is for each n belongs to Z plus, right? Then I want to change the variable here. For n plus n, I am writing m. n plus n is equal to m, my substitution. Cm divided by Cn greater than mu minus epsilon n what? N is equal to m minus n, no? For each m greater than or equal to n plus 1, m is at the most capital N plus 1. Thus, Cm greater than Cn m minus epsilon raised to the power m minus n for each m greater than or equal to n plus 1. Hence, Cm greater than Cn divided by mu minus epsilon raised to the power capital N times mu minus epsilon raised to the power m for each m greater than or equal to n plus 1. Thus, mth root of Cn, thus that is strictly greater than Cn raised to the power mu minus epsilon raised to the power 1 over m times mu minus epsilon for each simple n greater than or equal to n plus 1. Now you can see this is a constant raised to 1 over m is 1. So if you take the lim sup, not lim sup, lim inf, no? This is greater than or equal to, this is 1 mu minus epsilon. Since epsilon is arbitrary, lim inf m tends to infinity. Here there is nothing. You couldn't say I saw it equal. See m to the 1 over n greater than equal to. So we have completed the proof. I mean, this one always lim sup is bigger than or equal to lim inf. Always as a result, I have completed the proof, and this is very important result. You will be using it very often. Is that a problem? Okay, so this is very important. I guess he is using this to prove that limit of n raised to the power 1 over n is equal to 1. I guess that is how. But let me go back and see what he is. Okay, he proves this thing. Now we are on page 180. Ratio test. But do we have enough time for ratio test? No, not enough time. But root test is now clear, no? One thing you need to remember now, I said, you are given a series of non-negative terms, Cn, O, A, N, whatever I can remember the, oh, they are A, yes. If the lim sup of nth root of A n is strictly less than 1, the series sigma n converges. Greater than 1, n going, whatever the series diverges, if n is lim n is equal to 1, we cannot say anything. So if it is true for lim sup, it must be true for when there is limit. So you can say limit of nth root of 1 over n less than 1, then if the limit is less than 1, lim sup is already there. If the limit is nth root of 1 over n less than 1, then series converges. If the limit of nth root of n greater than 1, then sigma n diverges and equals 1 no information. So actually the other roots, they first do limit case. Here we started by lim sup. Yes, doesn't matter. So but without doing the 5.3 corollary, let us show that, I don't know whether we have to use that to prove it. We said an is equal to n. Let's see then. We will try. If it doesn't work, then it doesn't work. One day I was in US, one course, I think I told you something. My prof, there was a problem. Usually I do all the homework. I was doing my PhD. I couldn't do. That means the rest of the students also couldn't do. Then we asked prof to solve it on the board. He tried one method. It didn't work. No, this method doesn't work. Then he, let me try another way. Then he tried that. Oh, that method doesn't work either. So let's try this way. It doesn't work. So what's the next question? To this day, I don't know how to solve it. Now I cannot remember the problem. Anyway, this is a very important thing. You need to remember this. You need to remember. This from here, this is something you get. No, let's do it. What? Result. Prove that limit n tends to infinity, n raised to the power 1 over n is equal to 1. So let proof. Let a n is equal to n. For each n belongs to Z plus. Then a n greater than 0 for each n belongs to Z plus. Thus, lim inf of nth root of a n. Let me write this way. Nth root of let's write here. Less than or equal to lim inf of I thought you would see it. plus 1 over A less than or equal to lim inf of nth root of A less than or equal to lim sup of nth root of A less than or equal to lim sup of A plus 1 over A. Thus, lim inf of n tends to infinity n plus 1 over A less than or equal to lim inf of nth root of A, nth root of n less than or equal to lim sup of nth root of n less than or equal to lim sup nth root of not root n plus 1 over n. However, you know n plus 1 over n converges to 1. Therefore, lim sup is 1. No? Similarly here, both are equal to 1. Thus, since limit n tends to infinity, n plus 1 divided by n is equal to 1, we have that 1 less than or equal to lim inf of 2 nth root of a n less than or equal to lim sup of nth root of n less than or equal to 1. Here you have 1, over there you have 1, therefore all the terms must be equal to 1. Thus, lim inf nth root of n is equal to lim sup nth root of n is equal to 1. Lim sup both are equals, therefore limit is thus. Hence, limit of n tends to infinity nth root of n is equal to 1. So limit of nth root of n is equal to 1. It's kind of little bit difficult to believe. This means like infinity raised to the power 0 is 1. kind of difficult. Now when you say limit of nx is positive, this thing is equal to 1, it is like x raised to the power 0 is 1. So that is agreeable. This one is kind of on the fence. Okay, so I guess I proved that. Then he has a remark, in addition to the ratio and root test, another very useful convergence test is the integral test, I told you, which we will cover in proposition 11.6.4. So,
4 more.
eh?
4 more to go.
4 more to go. Then once you learn that, I will give you a bunch of problems. You don't have to really submit very quickly. Try to do series. So, but before that, tests are over now. Did I prove ratio test? No. Next. I am kind of silly. Anything you want to ask? Homework is going well. Eh?
We'll give it to you on Friday.
Okay. So now you guys are good actually. So if you do sequences, you have a good knowledge, definitely. And series, by 2 more weeks, you will be good. So that's part of analysis.
Stop the video.
Yeah, this one.